So, what shall we do right now? Do you want to do some exercises or new stuff? Have you had some time to finish exercises? Yes or no? No, no, not new exercises, just new stuff, like new content. But last day's exercises, have you tried to finish them? Is it worth to solve them now or not? I need some more yeses or nos. Yes. Sorry? Yeah, that one was harder. Okay. So maybe let's solve 1, 3, and 4, and I give you some hint for the second one. What about that? Yeah? Okay. Okay, so let's do that. So, oh, stop at projections. Here it is. Okay, no, spoiler. That's spoiler. Just in a moment, okay, at the end of the class. Okay, so, well, live coding is always a bit tricky, okay, but also fun to make mistakes in front of everyone, right? Yes? Okay, so, first exercise. So, do you want me to just go and do it, or do you want to tell me how to do it? What's best practice? First, let me create a copy over here. Okay, so let me save a copy. And here it is. So I have a copy over here, and I will close this one to not. And this is, these are solutions. Okay, here it is. Okay, so the first one is we want to implement the SAIFR model. Okay, so basic tool of programming is, well, I had just done something very similar before with SIRS over here. Not this one. Yeah, this one. Yeah, but later on, right? So solving a system of OGs, this one, okay? And I can just take this one here. And yeah, I think the version from the second notebook, I think, is easier, right? It already has the stuff here. Okay, so I just copied this guy over here. Yeah, and here it is. So this is the SIRS, and now I want the SEIRS. The difference now is that I have an extra class, so I have a new parameter mu. Maybe what I can do is, okay, yeah, you have to keep going between this and the other one, right? So from this stuff here to the, let me just check the parameter. So beta 2, gamma 1, omega 1 over 12, and mu equals to 1/4. Okay. Mu equals to 1/4. Okay. And now I have susceptibles, initial number of exposed is going to be 0, 1 infectious, and 0, right? So this is in this order here, right? SEIR, right? So this is the order here. Okay, it's important to keep this in mind, right? Okay. So here, what do I have? The first equation is beta s times I. Okay, I. Right. So, but I now is the first variable, not the second anymore. Right. So I have to change it here and here. Okay. The same term here and here. Okay. And now omega r, and r now is the fourth variable. Okay. So now this is x3, and I also change the corresponding term here. Okay? Okay. Yes? Okay. Now the second equation is not this anymore, right? So I don't have, well, the term here now is minus, the positive term is the same. but the negative is minus mu times E, right? Minus mu times E. And now I have a new equation that is mu times E minus gamma times this guy here, right? So, and now this is S2 over here, right? Okay, so a good check is the total population has to be conserved, right? Yes? So the total population has to be conserved. So the sum of all of the equations has to be 0, right? So in match all the terms to be sure that you didn't forget anything, right? So you see that this negative term is equal to this positive term is equal to this negative term, this negative term is equal to this, and this is equal to this, yeah? So just you don't leak population anywhere, right? So, yeah? Okay, and now I just call OD int with this, what? Oh, yeah. In the list of parameters, I have to add mu, okay? So mu is over here, and now mu is also over here. Ah, yeah. Wow, great, thank you. Yes, there's an OMA missing over there. Okay, anything else? The legend, right? So I need also an E over here. Okay, something else? Let's try and see if it runs right off the bat, right? So. And here it is. Of course, it's pretty clear that we should run for more time, right? So let's maybe 200. I don't know. Let's just try and see. Yeah. Okay. So this is it. Yeah, this is it. Okay. So if you got a plot that is similar to this one, then you know you're okay. Yeah. Questions? Comments? This was the easy one. Yeah. Okay. So let's go for the number 3. Number 3 is a bifurcation diagram of this model. Okay. So what I'm going to do is I'm going to, I don't need to copy this again, right? So I already have the SEIRS function defined, so I just need to copy the code for the bifurcation diagram. And it's not written here, but what I wanted actually was the bifurcation diagram for the, you see that for a long time, you have endemic state. So I want the number of infectious individuals for a long time, okay? I should be more explicit here, right? Because I would also do other stuff, right? So, okay, so this is exploring parameter space, and now, yeah, this is the old, right? So I use betas, and now I iterate over the value of beta, and then I plot the final value of I, right? So I just copy and paste this guy over here, and let's see how we have to adapt it. So this is a very large time, okay? So betas from 0.9 to 2, I think, yeah, it's okay. Let's go with this. I max here, beta, and now I just have to change this guy here, SEIRS. At 0 is already set at this new value here, okay, so there's no problem. And now I need mu here as a parameter as well. And I want the third column, right? So I want the column for infectious. So this is column 2 now, okay? And this is Imax, right? So I should actually use, I don't know, I final, right? So the last value for I final, and I don't want the maximum one. I want the one at the last moment in time. Yes? Okay, so now I use this guy here. I transform this, I convert this to an array. Okay, and I run this. And while I run this, I copy the plot here. Okay, because I think I opened, so how do I add more code here? And this is just I final over M. Okay. And here it is. Yeah? Nice? Yeah, questions? Comments? Issues? Yes. What kind of what? Sorry. Patterns. Yeah. Well, this is more of a programming exercise than doing actually full model analysis, right? So, you know, this is an interesting model, but it's pretty similar to the SIRS, right? So it's just that the incubation phase makes the curves a little bit different, and it adds a little bit of realism. But it's pretty similar in general terms to the previous model that we saw before, right? The SIRS model without exposed. Yeah? Yeah. Yeah, do you want to use the mic? No. Okay, so yeah, actually, I should have told you that there's a trick that we can use sometimes, right? So that may be useful. So you're saying in the first exercise, you were bothered by this stuff here, right? So the X0, 2, and no? Yes? No. Or on the bifurcation diagram. Where? The initial condition? Yeah, so this is a list with 4 elements, right? So the S, E, I, R. I don't know what's... yeah, you do need the mic, right? So, well, at least I need the mic, you know? So I can hear anything. Well, this one, yeah, work. Okay. Otherwise, I would do too much cardio going up and down.
So why in the letter E you put 0, and also in the letter R you put 0?
It's just because I said in the text over here that the initial population would be such that I think I thought with a single initial condition with a single infectious individual, and all the population susceptible. So like an infectious individual arrives, there's no one exposed just yet, right? So it will be after a very short time, yeah? Okay. As we can see in the solution, right? So we start, of course, in this scale here, we don't see much, but if you start very close here, maybe, let me do, let's do a zoom on this plot here, right? So this is from 0 to 5, from 0 to, yeah, this just makes a zoom of the plot, right? So from 0 to 10. You see, you start with one infectious individual, and it starts creating new exposed individuals in orange, you see? Yeah? Yeah. And then it leads to infectious individuals again, but then they are decreasing before starting increasing again, yeah? Of course, these are numbers less than 1 that don't make sense in terms of real individuals. Like what is a half an individual, right? But then this is, I think Roberto didn't discuss this much, right? The issue of using real numbers, using differential equations, it only works when you have large populations, and you can stop worrying so much about, you know, half individuals and so on, right? So at the very, very beginning of an epidemic, when we have only few individuals, perhaps you should take into account that individuals are are full are integers, right? But then this is an approximation that we can use because we're interested in what happens with the spread of the disease for larger numbers. Yeah? I think this is not your question, but yeah. Is it clear now? What you asked? Okay, okay. Okay, but I don't think this was actually a Python issue, right? I think it's more of a, yeah? Okay. Yeah, I think I promise you that I have a version of this in R, right? So I will post a link for that. Okay, I have a version, at least of this, the first 2 tutorials I do have in R. Okay, so I'll post this for people that prefer using R. Okay. Okay, so exercise 2, you had some more time. Do you have issues, questions, comments? Let's go for the last one. So now I want to see what happens when I vary both beta and mu at the same time. Okay, so I want to do that color map thing, right? So let's go to 2 parameters at once, and now I open this part here, right? So again, large time range. Now I don't want omegas, I want mu's. And what are values, reasonable values for mu, right? So that's gonna take us some thought, right? So 1/4 is like incubation takes 4 times as long as ovary, which is already a long incubation period. So we can try to use much smaller values and then go up to, no, much larger values, and then 1/4 is already kind of small, right? So we can go maybe from 0.1 up to 2, maybe something like that. Yeah. So this is kind of guesswork, right? Based on the relative time scales of gamma and mu, right? Because gamma is ovary rate and mu is incubation rate. Okay, so 1/gamma is the mean time for ovary, 1/mu is mean time for incubation. Yeah, so I will say that mu is between. Of course, and play with this, right? So we'll go from 0.1 up to 2 in steps of 0.1. This should be about 20. 20 is okay, right? So you don't want to put too many points here, otherwise this takes a long time. We don't need. Let me change this, right? So it's useful to know the shapes, right? So here it is. And now I need this line here, okay? Okay. And now I'll tell this by large M, okay? And now we want this here. Oops. Oh. Always something. Yeah. Muse, yeah. Here it is. So one has 20 or the other 19, this is okay. And IFP, blah, blah, blah. Now I want to change this to CIRS. This is B and this is M. Oh, sorry. I should need mu is here, right? So you have to always be careful that the parameters are in the same order as we had before, right? So this is beta, mu, gamma, omega, and m, right? So beta, mu, gamma, omega, and m, yeah. So beta, mu, gamma, this is omega that is now fixed, yeah? And m, okay? And I solve this and take the last value and save this last value, okay? I think at the end here, okay, it's already working. So this may take a little bit of time. And there's a bug over there. Oh yeah, there's an OMA missing here. Okay, and now it's running. And now the odes for plotting, right? So one useful thing here is if you put a lot of points into these guys here, the odes can take quite a bit of time to run, okay? So it's usually useful to separate the code for running this slow step and then another block to plotting, because then you can mess with the plot without having to recalculate everything. Yes? Down, yeah. So I need... you're right. Yeah, you're right. So, I had to run everything again. Okay. Yeah, but it's going fast, right? So, yeah. And this now is mu. Okay. And here it is. Yeah. I don't know. It is more interesting than before, right? Of course, as you increase beta, you are always seeing an increase in the endemic population, endemic prevalence of the infection. But also as you increase mu, that is, when you reduce, increasing mu means reducing the incubation period, right? So if you reduce incubation period, you also see this effect of increasing the prevalence, okay? But this value saturates, you see? So it's much more marked here, close to 0.1, 0.2, 0.5. And then for larger values of mu, this doesn't change so much, okay? So this, you see that this effect end of saturates, okay? Yeah, nice. Yeah, so that's it, right? So now the second one, right? So the second one I'm not going to do right now, but I'll give you some hint, okay? So what's the issue here? We want to count the number of new cases, okay? And what is the problem? Beforehand, we had done that in the SIR model, we had done that using the difference in the number of susceptibles from one time to I don't know, up to next week, okay? So I count susceptibles today, susceptibles in a week, the difference is number of new cases. But now in this model here, the number of susceptibles, the difference between the number of susceptibles happens because of two different processes. New cases, but also recovered individuals that become susceptible again. Yeah? So the difference between these two values reflects not only new cases, but also loss of immunity. Yeah? So if you just do this difference, you are undercounting new cases. Yeah? Okay, so you cannot do that. But then you think, okay, but what if I use the E value, okay, the value of E, of the exposed, okay? Exposed has the same issue because the number of exposed individuals changes because of new cases, but also because of individuals becoming infectious. So if you count the difference in this number after a week, you see the difference due to these two processes at the same time, okay? And the same for I and the same for R, right? So none of these four variables do the job that I want, that is counting new cases, yeah? So what do I need? I need a variable which changes only due to new cases, yes? Yeah? So I just include this variable in the model. Yeah, and so I want to have new variable whose only change is number of new cases, right? And what counts for new cases in this model here? So cases here is usually after incubation period, right? So the rate with which new cases accumulate is actually mu times E, yeah? Mu times E, because these are incubation, individuals becoming infectious, yeah? Okay, and I won't take questions for this, okay? So you have to take this hint and think a little bit more, okay? Okay, so that's it for now. And now let's change pace a little bit. So I have a new notebook here, okay, for today's class. I'm not sure if we can go over everything, but it's already on the ICTP webpage. If you go here for class 3, is over. No, sorry. Class 3, class 3. Over here, attachment here for class 3. Okay, so it's this notebook here. But before doing that, I want to do some stuff on the board first. Okay. 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 So what I'm interested in doing now is working with what we used to call structure models. Okay. So what is a structure model? This is a little bit different from, for instance, adding an exposed compartment. It's not just that you are adding more compartments, adding more stages, and so on. The idea is that the population itself has some structure, right? So in the very beginning, when we were building the SAIFR model, a big assumption is that infections here, this guy here, the population is well mixed. Yeah, the population is well mixed. Everyone interacts with everyone with the same rates. Yeah, with the same probability. Yeah. Okay. When we introduce a structure, we are kind of relaxing this a little bit. Okay, we are going to say, for instance, if you have age structure. Okay, age structure is like we have small children, you have older children, we have teenagers, and then you have young adults, older people, and so on. Okay, and of course, they are not really well mixed. Yeah, because children, school-age children, interact a lot more among themselves than with adults. So most children have a lot of interaction only with their parents and maybe their teacher, with adults, like day-to-day, yeah? But they interact with a lot of children, yeah? And they interact very strongly, yeah? Does that make sense? So it doesn't make sense to say, well, you can do models without age structure, but depending on what you want to think about, it's useful to structure a model, for instance, by age. Yeah? Yes or no? Yeah, makes sense? Yeah? Okay, makes sense. So how do you do that? Yeah? So now we'll have to rethink our whole model structure. Okay? Rethink our whole model structure. So yeah. So yeah, I should yeah. Yeah, okay. Okay, so let's think of the susceptibles, for instance. Okay, now I have what? Suppose that I'll should not make too many classes here. I'll just say 4 classes, right? Children, children up to, I don't know, 20, and then young adults, older people. Yeah, 20 years. Okay, classes. So I'll have 4 classes of susceptibles. Yeah. So I will have S1, S2, S3, and S4. Yes? And each individual in those classes can get infectious, yeah, can get infected, and then recover. So we have this process here. Yes? But for each of the classes. Okay, I'm going back to SAIFR model here for simplicity, okay? But this is not really dependent on the structure of the model. You can do this for SEIR, SEIRS, anything else, right? So just the, right? So we have this. Yes? Okay. So, but what's the point here? The point is this process of infection here, the process of infection, it's not true that children only interact with children. So I cannot build 4 different SAIFR models. Yes? If the compartments were completely isolated, if they are like cities that are completely isolated, for instance, like this is one place, another place, and so on, this would be 4 different SAIFR models. Yeah? But this is not the case because children can get infected by adults. Adults can infect older people, and so on, yeah? So what do? You write something like this, right? So I write something like this, and now I need some notation as well, right? So I instead of now, of course, I don't want to write 12 equations, right, by hand. Yeah, there are 12 equations still, but we don't want the notation. I don't want to write 12 equations in the board. Yeah, okay, and neither do you, I hope. Yeah, okay. So I'll say that I will look for SI here. Okay, so SI dt is going to be minus something that I'm going to call the force of infection. Okay, the force of infection, that is lambda I SI. And this force of infection here, okay, has contributions from all of the other classes. Okay, so what is going to be lambda I? Lambda I have to sum the infectious individuals for IJ here, the infectious individuals of all the other classes, right? What else is missing here, right? I need to divide by n and multiply by beta. Yeah? So beta is contact rate. Okay, so as I just told you, we don't expect contact rates to be constant between classes. So like, I don't want to just do this here. Why? Because the probability or the contact rate of children with children is different of children with adults, children with older people, and so on. So this is actually written like this. Oops. Beta I j. Yeah? Because it's a different number for each pair of classes. So far, so good, people. Yeah? Questions? Objections? Not yet. Okay. Okay. We could discuss, and this is kind of funny, right? We would discuss if this should be symmetrical or not, right? Because it's kind of funny, right? So because beta ij is the process of individuals of age less j infecting individuals of age less I. So for instance, beta 1, 2 is adults, infectious adults, infecting children. Beta 2, 1 is infected children infecting susceptible adults. Okay? Should this be the same contact rates? And the answer is no. That's funny, right? But the answer is no. Okay? And this is from an empirical point of view. Okay? We'll talk about this in a moment. But there's something else still missing that we had in the SIR model. That is you have to divide by n here, okay? By the population size. And what is the population size that I should use? Because, okay, in the SIR model, let me write this. The SIR model, we had something like this. We had this. What was the logic? We have, for instance, an infectious individual that has an contact rate of beta with other people, and the chance, S over N, is the chance of this contact being with a susceptible individual. Yeah? So if we think in these terms, an infectious individual having a chance of what is the chance of the person contacted being susceptible? Then you have to divide by the class of the person being infected. Yeah? So we have to divide this by Ni. That is the class being infected. Yeah? But you can also think on the opposite side and think, okay, no, beta is this is the number of contacts of the susceptible individuals. Yeah, each susceptible individual has a certain number of contacts, and it has the chance of, yeah, it essentially boils down to this. I can think of this in this way, or I can think of this in this way. Yeah? So if I think of this in this way here, yeah, so I have susceptibles having contacts, and what is the chance of finding an infectious individual? Yeah? If we think about this in this way, then here I should be dividing by the number of individuals in the infecting class. That is the class J, not the class I. So instead of this, I would write, oh, and J. Yeah? Okay, so now the question is, this will lead us to different models. Yeah? These models are actually different, okay? They're not the same model, okay? They will be slightly different. In practice, most of the time it doesn't make a lot of difference, okay? But this has not been as well explored as I would like, okay, in the literature, okay? I think most of the empirical studies that analyze this tend to use, which one again? So, I think they tend to use this one here, okay? Susceptibles. No, I don't remember which one. Okay, so I have to check, okay? So I'll show you some reference later on, and then we can talk a bit more, okay? But is it clear so far, people? Yeah? Yes or no? Questions? It is a little bit weird that we have some arbitrary choice here, seemingly arbitrary, okay? But modeling is choices that sometimes reason them very clearly, sometimes it's not so easy, okay? Okay, so, well, the rest of the model is more or less directly, right? So we just define lambda in one of these two ways, okay? And then we just write down the equations as GSI dt is minus lambda I Si, and then GII is lambda I Si minus the over rate, gamma I, and GRI dt is gamma I over here. Okay. Okay, and this is a set of three equations times the number of classes, okay? So this is actually, I wrote it pretty much, it looks just like the SIR, okay? But the difference is that inside this lambda here, we have this stuff here, okay? We have this matrix that connects all the equations together, okay? Okay, so you see, of course this is simple to look at. And you see that you can write it in this shape here, in this form, regardless of the number of classes, okay? So instead of 4, I would use, I don't know, 20 classes, right? One at each 5-year age, right? That we have in the census, for instance, okay? And this means that you suddenly are working with 6 situations, yeah? And then you can use this to impress your friends, right? You can say, oh, I just wrote a model with 6 situations. And then they will open their eyes and, whoa, how? Okay? But this is actually simple, okay? Okay. What else? We can also use this. This is also very useful if you have different, because now the only difference between ages is actually here, okay? Is actually here. We can show that if this beta here is an homogeneous matrix, like all of the elements are the same, this is completely, this would give the same results of the basic SIR model, okay? If all the connections are all the non-touch rates are the same, okay? This I think we can prove this mathematically, okay? We can we recover the basic SIR model, okay? So all the difference from the SIR model is inside this matrix here. Okay, but we could also add some new stuff, okay? So we can say that individuals from different age classes, different ages, have different responses to the disease itself, for instance. Okay? So we would, for instance, say that individuals from certain classes are more or less susceptible to getting the disease, so we would multiply here by susceptibility by age. We would say that gamma recovery rates are different depending on age. If you had more compartments, for instance, if you have compartments for severe cases, for instance, okay? This is very important, for instance, for flu, okay, or COVID, right? We want to be able to account for the fact that older people are much more prone to being hospitalized, having severe cases, dying, and so on. So if you include this stuff in your model, you have parameters related to the risk of severity. So you have another class of, I don't know, mild cases versus severe cases, and the probability of an individual developing a severe case is going to be higher if they are of certain classes, okay? Certain ages. Okay, so this is also very important, okay? But in the basic SIR model, we don't have this, okay? Questions? So, okay, so now let's solve this model. And as you can see, of course, we are not going to be writing situations by hand, okay? So, yeah. So, let's do right here. Okay, so how we do this, right? So I have some text here that more or less explains what I just told you. Okay, so I have these 20-year beans here, okay? One thing that I didn't, I'll do for this in a moment. So let's try to implement this, right? So here is the model I just wrote on the board, okay? And here I think I used the one on the top, okay? So this is probably the most common one, okay? I always have to check which of those two are the most used, okay? And there's a reason for that, okay. Okay, so this, I think I use kind of real-like data here. So this is population for São Paulo in 2021. I don't know, this is from the last census, probably. And here, you see, first of all, I don't have just the total population N now. I have 4 classes, okay? Population of people up to 19 years, 20 to 44, 49, 50 to 69, 40 to 59, and 60 plus, okay? So 4 population. So I need more information from the population, okay? I need the population stratified by my structure, okay? And now I need to define the initial condition, okay? What is the initial condition? Well, the initial conditions, I need to have everyone in susceptible infectious and over. So I use, this is a funny function here, okay? That I just put together these 3 arrays here. So the first array is the array of populations. The second one for infectious are just 4 zeros, so this is an array of 4 zeros, and once again the same for the overt, right? And then I put, and this guy here is what? Is an array with 12 numbers, okay? So because remember that OD int, right, when we go here, it receives just a single array, okay? So what is the trick here? The trick is that I have one vector for susceptibles, another for infectious, another for overt, okay? So this is 4 numbers, another 4, another 4. I have to put all of them together in order to pass to the integrator, okay? So my function will still work in the same way. I have x being everything together, okay? So what do I do to make this manageable is that I'm going to I start composing it from the 3 classes, then I pass it to the integrator, and then inside I'm just going to split them again in order to be able to work with them. Yeah? So let's see how this works. So here is the part where I in the S0 here, this is how I put it. I put them together, okay? I put them together like this. I just this is a concatenation, right? I concatenate all of them together. Now I will take one individual that is infectious from the, so this is the class, so this is the second class of infectious, okay? Yeah? So this is an adult, someone from 20 to 39 that is initially infectious, okay? So I had to take one out of the same population of susceptibles, okay? So I took one, yeah, okay? And this is the, let me run this. This is the initial condition, okay? And you see here that this is how I split them again, okay? So I have this initial condition. I use this function. So this is the initial condition, okay? This is 12 numbers, okay? And you see that this number of susceptibles here, the first 4 numbers, is pretty much what I wrote up here, okay? With the difference that I took 1 from here and included here. You see 1 over here. So how do I I'm really going to work with this later. We're going to take at 0 and split it into 3 parts. And these 3 parts are going to be S, the vector S with 4 elements, the vector I, and the vector R. Okay? And now if I print this I here, you see it's 0, 1, 0, 0. Is it clear, people? This is really important to get clear because otherwise your minds will not over later. Okay? Yeah? Okay. Yes. Sorry?
In this case, we're putting the first infected individual in the 20 to 40 age.
Yeah, exactly. Yeah. Could be another one, a different one, but yeah. Arbitrary, okay? Arbitrary. Okay. So far, so good. Questions? Okay. So now we write the model equations. Okay, so this is the time. And here I use this particular contact matrix here that I'll talk to you about it in a moment. Okay, but where this comes from? Okay, there's a famous paper that does this kind of stuff. But let's look at and this is based on is empirical data, but it's an actually an extrapolation using statistical models. It's kind of complicated stuff. But because this is not data collected in Brazil, in São Paulo, or whatever, right? So it's data from other places, but they use some ways to try to extrapolate it to many places in the world, okay? But let's look at the shape of this, right? So even if this may not be exact, okay, this helps us to have a sense of what does this what does an untouched matrix look like? Okay, so you see here is 0. It's the first age class, so this is children, and then children up to teenagers, if 0 to 19. Okay, and then the second column and line are 20 to 49, and so on, so on. Okay, and this is so this bright yellow here, the largest number, is untouched of children with other children. Okay, well, not children only, right? Children up to up to 19. Okay, yeah. So this is the largest value of the whole matrix. Okay, and you see that this matrix is kind of diagonal here. Okay, it means that people tend to interact more with people of similar ages. Okay, and off diagonal, okay, is untouched across age classes. Okay, so children with younger adults, children with older adults, and here as well, okay? And then older people in general have less untouched with other people, but it's still, yeah. And you see here that this is pretty much working age, right? So 20 to 60, and this is more homogeneous, right? So after you enter the work world, you kind of interact more with people of different ages, but that are also adults, okay? Yeah. Make sense? Yes. Sorry?
Shouldn't the matrix be symmetrical?
Oh, so, well, I told you a little bit about it before, right? So the answer is no, right? Because, well, it is pretty symmetrical, okay? But it's not perfectly symmetrical. So the thing is, we have a classroom full of children, okay? So, and you have one teacher interacting with, I don't know, 30 children. Is it really symmetrical? Yeah? So, you see what I mean? Yeah? Of course, it's kind of symmetry, but not completely symmetry, yeah? You are interested? Oh, okay. Okay, so is it easier to understand now? Yeah, I think this is very nice to look at this stuff. Okay, okay. Now we have a contact matrix, but the thing is the beta value. Okay, I wrote it like this here. Okay, this is just the matrix here, but actually you remember that beta is contact multiplied by the probability of contagion for each contact, okay? So we usually take this contact matrix over here, and we multiply by a constant that is related to this probability, okay? So we always have to end of, this is not the beta itself, it's a contact matrix that still has to be multiplied by something related to probability of infection or susceptibility and so on, okay? So, here I chose this number here that I called B0, and beta is going to be this B0 times the contact matrix, okay? It doesn't change it changed the scale here, but it doesn't change the shape, all right? So and gamma, okay, here I used a gamma that is age dependent, so I said that older people take longer to recover, okay? Just to, yeah, all the other classes are the same, okay? So this is, if this is in days, I think this should be in days, okay? So this is, yeah, this B0 can also account for changes in time scale, okay? Because the contact matrix it has dimensions of time inside, yeah, because this is a rate of contacts, okay? So if you change your time scale, you have to include something in B0 to account for this change in time scales, okay? Okay, so this is our model now, and you see that I have beta, but you see, beta is no longer a number. Beta is a matrix, but it's okay. The numerical integrator takes arguments here, parameters that are not only numbers, but also vectors, matrices, and so on, okay? So this is the matrix beta, gamma is this array here, and age structure is our number of people. That is, I wrote it up here, right? So, oh no, I didn't. I didn't. Ah, okay, I'll call with this, okay. The age structure, so it's the number of individuals per age class, right? So here, when I call it like this, you see, yeah? Beta, gamma, and the population structure for São Paulo here, okay? Okay. And what is inside here? So you see the structure is the same, X, T, and the parameter list, okay? X now has all 12 numbers. The first thing I do is I split it into three vectors here, okay? Now S, I, and R, each one of them is a vector with 4 numbers, okay? And now I calculate lambda, so this dot here is just the usual matrix product, okay? Matrix product of beta times I. You see that that each line in this matrix product is going to be this sum here, okay? I can open this later if we have time, yeah? Yeah, let me not lose notion of time. Oh, no, yeah, I have time. Divided by the population of each age class. Okay, so this is with the top form over here, okay, because I divided it outside. You see that I multiply first and then divided by the age structure. If we wanted to do this down here, it would be a little bit different, only because I would have to divide I by age structure. So it would do something like this, you see? So it's subtle, so you have to pay attention not only to which version you are working with, but also that your code reflects the choice you made, okay? Okay. So I'll stay with this. Okay. And now the derivative of susceptibles is just minus S times this lambda here. Notice that I cannot write lambda because lambda is a reserved, lambda is does something in Python, okay? So we cannot use this, okay? S times lambda, GI is just S times lambda. I think I didn't use sigma over here, okay? I forgot about it, but it's just another parameter that I would use. S times lambda minus gamma times I. And you see that all of these are vector operations. So this is a vector times another vector. It means that I'll take the 4 numbers and multiply element by element with the other 4 numbers. Yeah? Okay? And finally, GR is gamma times I. And so I have these 4 vectors here that are the derivatives for each of those classes. Okay? And finally, at the end, I have to put them all together, okay, and return all the derivatives in a single vector again, okay, in the same order that I received it, so S, I, and R. Yeah? Okay, so this is a bit complicated. A little bit? No? Questions? Comments? Okay, okay. So, yeah. Now that I define this function, the rest is the rest is pretty simple. Yeah, there's an no, sorry. Yeah. So the rest is pretty simple, right? So I just OG int to solve the model with that initial condition that I had already defined. I think the time is defined up here. And then the list of parameters. Yes. Sorry? Yeah? Yeah, I calculated it here, yeah? So it's the product of beta times I divided by age structure. Yeah, I don't need anything else besides beta, gamma, and the age structure, right? Yeah? Okay, so let's run this. And now what the solution? You see the times here were from 0 to 90 steps of 0.1. This is 900 steps in time, okay? So what is the shape of the solution? This is 900 by 12. So I have 12 columns, okay? 12 columns, because I have 4 susceptibles, 4 infectious, 4 overs. Okay? And if I try to plot as before, well, this is a mess, right? This is a mess. Yeah, everyone agrees this is a mess. Okay. What is going on here? I should have labeled this, but I'm just too lazy to do that. But this is S0, S1, S0, no, S1, S2, S3, S4, E1, 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 E2, E3, E4, R1, R2, R3, R4, right? So everything mix it up. But this is not very useful, right? Not very easy to look at it. So the first thing that is really important is much easier, because you know, we do have the number of people of each age, okay? So total number of people infected in each class is not so nice, because you don't, you know, there are more, I don't know, I already forgot, right? So what is the age structure that I used here? Let's go back there. I have a little bit more young adults and quite a bit less older people. Yeah, so of course I expected to have more infectious individuals in the 20 to 39 than in the 60 plus, right? But it's harder to get this into our heads, okay? So it's much better when you do this to do what? To look only at the incidence or the prevalence per number of people, okay? So I have to take the numbers of susceptible, infectious, and over divided by the population of that age class. Yeah? Makes sense? Yeah? So I won't work with absolute numbers anymore, only with the prevalence per population, okay? Per population. So what do I do here? First, I take this S, that is the solution, and I split it in 3, okay? Split it in 3. Beforehand, when I did it here, X was a single dimension, okay? It's just a vector with 12 numbers. And dividing it by 3 in 3 is, there's no ambiguity, right? I just take 4, 4, and 4, yeah? But when I have this S that is 900 by 12, when I tell it to split into 3, I would split it into the 12 columns into 4, 4, and 4 columns. I would take the 900 lines and say 300 lines, 300 lines, 300 lines, yeah? Okay, so I have to tell it to say, I want to split by the columns, okay? I want it to split by the columns. So I have 4 columns, 4 columns, and 4 columns, okay? Okay, and now the small s is going to be this s divided by the population structure. So I take each of the columns here and divide by the population of that age class, okay? And the same thing for I and R, okay? And now, now I have everything the way I want it, okay? So I have susceptibles per age class and so on, okay? So I would do 3 different plots, one for each compartment, okay? One for susceptibles, one for infectious, one for over. And I do this with this subplot here that creates, as the name implies, right, subplot, right? So let's run this. So this is susceptibles. They start all of them at 1, like everyone is susceptible, and then they decrease here, okay? Infectious goes like this. And you see that, remember that children are the class with more contacts, yeah, between themselves. So they go up a little bit faster, yeah? And then you have pretty much the green and the orange are pretty low, and the tree here that is older people, 60 plus, is down here, okay? So the higher your contact rates, the faster you get infections, okay? Of course, this is not a huge difference, okay? So this is just a few days here, and this is A of time, but anyway, okay? What else can we see here? And you see that the final number of overs, okay? This is pretty much homogeneous, okay? It didn't make that much difference in terms of the proportion of people that end up infected or not eventually, okay? Just on the timing that it happens, right? So the disease spreads faster in children first, okay? Questions, people? So, questions? Let's think about it for a moment, right? So, okay. Okay. Let me run a slight variation of this, okay, with the different model structure, as I told you with this model structure here, just to check that it doesn't make much of a difference, okay? I told you that, but it's always nice to prove it, right? So to be able to look at it and be sure that it doesn't matter so much, okay? So this is the raised plot, and this is, older people here took a little bit longer now. The curves are more separated and so on, but other than that, for the final size and so on, it's very similar, yeah? Very similar, okay? But there is some difference, okay? They're not the same model, okay? Okay. Yeah. This one. Okay, yeah. Oh, I see. Okay, I had the difference in the axis scale here, yeah? Yeah, I forgot about this. You see here that I did a zoom in into this region here. Okay, let me plot again, sorry. Yeah, this is the full, oof. It's kind of weird, right? Because it looked like it was it, right? But you see, this is the full dynamics, but I had zoomed in into this region to see that what happens very close to the peak here. Yeah, we should probably have noticed this before, right? So, and this only when you zoom in that it becomes very clear this difference in timings. Yeah, if you look from far away like this, yeah, you can see that there's a difference, but it's not that much, right? So in this time scale of, I think I thought of this in terms of days, right? So this is like 3 months, okay? 90 days. Okay? Good, so let me go back to, okay, so now I want to do another example, okay, another example. And now I want to think not in terms of population structure in terms of age, but in terms of space, okay? So, so instead of, I won't try to redo everything here, but I just want to, because I'm pretty lazy, okay? You can see that yeah, I do the minimum, okay? So instead of thinking of this now as ages, right? And think of different subpopulations. So you can have, for instance, some cities, right? Some cities that are not, that are more or less close, but they're not like the same city, right? So there are different urban areas, and then, of course, people travel from one to the other, right? Yeah. So there are connections. There are people that may carry the infection from one city to another. Okay? Yeah. Then what happens? Instead of having four different SIR models, I can say, well, the cities interact. So I will put all of them in a model, in the same model, and model the connection between the cities, okay? Is that clear? Yeah, so the idea is pretty much the same. I have what happens in city 1, in city 2, in city 3, in city 4, and so on. Okay, I have the total population in each of the cities, okay? And now my beta is no longer a contact matrix. Well, you can call this a contact matrix, but you can think of it in terms of what is the probability of travel between cities? Yeah? So what this term here means is an individual from city J traveled to city I and infected some susceptible in city I. Yeah? Okay? This kind of stuff, it tends to be also really hard to get data about. And you can think about this in several different spatial scales, right? And think of this in terms of a regional scale. For instance, if you think of traveling via roads and buses and so on. Or you can also think of this in national or global scale. If you think of people being connected via airports, via planes, okay? And then you have some proxies for these contacts via number of people traveling via plane between different countries, different cities, and so on, okay? So you have several modes of transportation, and each of them will lead to different ways to estimate these contact rates. Yeah? Make sense? This is simple the way I'm talking, but it's really complicated in practice, okay? But yeah. Okay, and then the model is exactly the same. Yeah, this is funny, but the model is exactly the same. And once again, we have this stuff again, right? There's two ways of modeling it, because you can think of an infectious from city J going to city I and the probability of finding a susceptible there, or you can think of a susceptible that travels to city J and the probability of being infected there. Okay, so it's perfectly analogous. Okay. But now that we have done this model already, the implementation is exactly the same, okay? The implementation is exactly the same. So you have, let's see. So the model is pretty much the same, you see? And now it makes a little bit less sense to change, for instance, gamma that we were saying the over rate, it doesn't make a lot of sense to say that people in a city over faster or slower than people in other cities. Okay, so usually we use the progression of the disease is usually homogeneous across different cities. Okay, unless we have something really weird, right? So I don't know, treatment in one city and not in another. I don't know, something really weird. But for instance, if you include vaccination, for instance, okay, part of your population is vaccinated. So you say, well, part of the population initially is already re-overed. Okay, you can have initial conditions with different proportions of re-overed in each city. Okay, for instance, you could use that in your model. Okay, could include that. Okay, so here these are just guesses. Okay, these are not real cities. I just guessed 3 different cities with different population sizes, a larger city, smaller, and a small city here. And now I do the same trick. I'm going to put them all together into a single vector. Okay, so these are now 3 cities, so I have 3 numbers here, 3 numbers here, 3 zeros and 2 zeros, and I say, well, at the initial time, 1 individual from the first city is infected, okay, from the first city. Okay, and now I have the times here, and now I have to build the contact matrix again, right? So to build the contact matrix, I will say that I will start this matrix with this. This is an identity matrix, right? So this is what this I function does. Okay, this I function just build an identity matrix. Okay, and I'll say that what I want is I want to say that some people, instead of staying here, are going to stay sometime here or here, okay? And then I'll subtract from the main diagonal and add to the other terms, okay? And this stuff here, this is interesting, right? Because these 2 guys here, okay? They are the connections between city 1 and 2. And these guys here, connection between cities 1 and 3. And these guys here, connections between cities 2 and 3. Okay, and this, you can think of this as a network. Okay, so this matrix represents the contact network between cities. Cities that are very connected, that has a lot of people traveling between them, have larger numbers here. Okay, and cities that are very far apart, either by distance or I don't know, there are no flights that connect them or something like that, have low numbers here, okay? Of course, one thing that you have to be careful is that the main diagonal is always going to be much, much, much larger than the terms of diagonal. It's much more common to contact people in your own city than in another city, okay? Because most people don't travel like every day, yeah? So, okay, now what do? I set something like frequency of travel being 0.001, and I say that my contact matrix now is, oh, I did some trick here, okay, just, yeah. I will print this and show you, okay, so, yeah, let me print this guy here, okay. So this is this guy here, diagonal matrix, and this is what I did here. Okay, so here I subtracted this frequency travel from the main diagonal. So the I here is 1 minus 3 times frequency travel. So this is 998, and then I sum back this to all the terms. So all the off diagonal terms here is 0.001, and I think I did this wrong because this should be 4, right? So the sum, oh no, it's right. The sum over all columns is, right? So this is just to make this, I don't know, normalize it, okay? Yeah, this is just a trick to get these matrices here, okay? So this is strongly diagonal, but I have small values of the diagonal here that is the connection between the cities. So far, so good? Questions? Okay, and now beta, once again, this is connection, and now I have to multiply by the actual contact rate between individuals and probability of infection, right? So I just multiply this guy here by this B0 that is the actual beta here, okay? And now my on-touch matrix now is pretty much pretty simpler than before, right? It's just homogeneous outside and strong values only on the main diagonal, okay? Okay. Now I set a value for gamma, and my SIR model now is exactly I think it's exactly the same, yeah? Yeah, it's exactly the same, okay? Yeah? I think I probably copied and pasted and changed the name of the age structure here, and that is now the populations of the cities, okay? Okay, and now I just solve the model, okay? Run the model with beta, gamma, and pops over here. And the plot, I'm already going to do... okay, now, you see, beforehand, I was looking at a single population divided into age structures, okay? Now it makes sense to say, well, I actually want to look at each city and not at susceptibles, yeah? Susceptibles from the 3 cities. You see what I mean? Yeah? So instead of splitting in the way I had before, I'm going to do something kind of funny, okay? So here is the same code as before, okay? So this is, below here is the same code as I used for age structure. So it leads to this, right? So this is susceptibles in the first city, second, and third, okay? So it starts in the first city, and then the second, and then the third, right? Why does the third one grow faster? It's probably related, cities 1 and 2 here, orange and green, they are not the same because they have different populations, okay? Different population sizes. But the first city is the one where I included the initial infectious, okay? So the disease should spread there first, okay? Okay, but this is the same plot as before, but what if I want to look at the SIR solution for each of the cities? Okay, this is the first plot that I have here. So this uses a trick here. So this is all the elements of S, all the lines, and here I want the columns at each 3 values, okay? So I take 0, 3, and 6. And here is starting with 1, I take 1, 4, and 7. And here I take 2, 5, and 8, okay? So this is a trick to have the S, I, and R of city 1, S, I, and R of city 2, and S, I, and R of city 3, okay? And now I have this plot here with 3 different SIRs, okay? So they're pretty similar, and what we saw in the other plot that actually you have infectious in the first city a little bit further, a little bit earlier, okay? So 2 different ways to represent the same solutions. Questions, people? So this is the very basic stuff. I didn't try to model any specific network of cities and so on, just everything is kind of homogeneous and so on, but it already tells you how to work with this kind of stuff, okay? I have a reference here, and I want to talk a little bit about it, okay? Yeah, I'll go back to this on it later, okay? That is this paper here, where I got the on-touch matrix, okay? So this is actually, I think, the 3rd paper in a series, okay? But how do you measure on-touch matrix between people of different age classes, right? You actually, of course, depends on the disease, okay? If you are thinking of diseases transmitted via direct on-touch is one thing, via respiratory diseases is a different thing, sexual transmission is yet another different thing, okay? So, because, you know, depends on what you mean by contact, okay? These people have, that have focus on respiratory transmission, okay? So from being close together in an enclosed space, okay? And they had some data for doing interviews with people. So you go to places and you interview people and say, how much time is spent with which people and so on, what are their ages. And they did, this is actually at the end of social science job, okay? You have to interview people and then build a lot of data on how much time people spent with other people of different ages, and they did this looking at different settings where people interact, so at home, at work, at the school, at, I don't know, commerce and other places and so on, right? So they built this, and then, of course, they had this only for some countries, for some places, but then they tried to extrapolate this based on different populations structures in different places, like the age pyramid of each place, but also things like the mean number of students per class, or the mean number of people in households, for instance. Some places have much more people living together in the same household. Some places have fewer people, and so on. And this varies a lot from place to place, from county to county. And so they try to correct for this, to adjust their on-touch matrix for each country. Okay, so this is the main reference. This is I think it's some reference that is useful to have. Okay. Okay. That said, let's just a final comment here is, what do you have? What do you do if you have more than a single structure? Well, you can keep going. Okay, I would have a structure in terms of age and space at the same time. Yes, you can. Now you have 4 cities, 4 age classes, so you have 16 classes. Okay, the difficulty with this is actually how to parameterize this. Okay, because when you have a basic SIR model and you know gamma, you know lambda, the only 3 parameter that you have is beta, and kind of, if you have the time series, you can fit beta with the data you have. But when you have a contact matrix, okay, suddenly you don't have a single value to fit. You have, if you don't have any information on this contact matrix, you have, I don't know, 16 values, or if this is 20 by 20, this is 400 values. You don't have enough data to fit the whole on-touch matrix, okay? So you cannot really get this only from epidemiological data, right? And so what really restricts us in terms of adding more and more structure to our models is really data limitation, okay? It's not that the models are much, much more complicated. They are more complex in terms of having more equations, right? But the structure is the same. So the issue is really one of not having enough data in terms of what are the stratifications, right? And what are the contacts between each classes, okay? Each of the classes, yeah? Okay, final questions. Comments? Okay, so before finishing, right? So, well, actually the class is finished, right? But we are finally reviewed the topics and the groups, okay? So, we should put this on the web page, right? So I write to Thiago in a moment, right? So here it is. Here it is. Okay, so these are the groups and projects. I'm going to put this link on the course web page. Okay, so because these are the links to the projects. Okay, so these are the 5 groups. So we have a topic here on mpox, another one on avian influenza. You think more or less, yeah. Roberto, yeah, let's do the following, okay? So so you can save this for your, yeah. So you can access right now, okay? So yeah, everyone can see. Yeah, so open this on your phones and already have access to, or your computers and have access to the topics right away, right? Because I don't know, people have done for lunch, and then you can find your team members right now, okay? Sorry? I didn't follow. Sorry? Ah, okay. Oof. How do I do that? Sorry. I could do that with the original link as well, right? So I don't need this stuff here, right? So yeah. Does that work? People can point to that and works? Yeah. Nice. Yeah, everyone already got it? Yeah? Yeah? Okay. So this is it, right? So we have 5 groups, mpox, avian influenza, and in each of them we have a brief introduction to the topic and some questions and suggestions and what is your goal for today? So you have to meet with your team, okay, and try to understand the project, okay. What is it about? What is it you're trying to do? Today you don't have yet to formulate models or even you don't have to decide anything. You just have to read the text, read the references, talk among yourselves, and at the end of the afternoon, we'll have a very quick presentation from each of the groups, right? So only 5 minutes for each group, just to say, well, my topic is this disease, it works like this, the kind of question we are interested in is such and such question, okay? The questions we have here, okay, they are suggestions, okay? The topic, the project is yours, okay? It's not ours. This is not a, the exercises that I asked you to do is actually, it's just an exercise. It's just do this and there's a specific solution that I'm expecting, okay? There's one correct answer. The projects are not that. They're not exercises. They don't have a fixed answer. You can propose any question about a topic that interests you, okay? It's open, okay? We provided some questions, some suggestions, just to give some guidance, okay? But you can make other questions, you can refine these questions, you can change these questions, right? But the point is that we want you to, during the week, right? During the week, to formulate models, to try to attack to find some answers or some explanations related to questions that you have about the system, okay? Yeah, is that clear enough? I don't know if Roberto wants to explain better this stuff, or is it clear enough? I don't know. We have the whole week to go over this, okay? So this is, I think, actually the main part of the course, yeah, the projects, okay? So the dynamic is that we have every afternoon to work on this throughout up until Sunday, right? So on the Sunday morning, we have presentations. Usually we have some 20, 25 minutes for presentations on the Sunday morning, and we will follow you along, right? So we have 2 monitors over here. So Eric and Tomas over here that are previous participants in this course, and they are going to help you also to to any problem you have, okay? So problems with codes, problems with reference, problems with questions, problems with anything at all, okay? So they're here to help, okay? And me and Roberto as well, of course, okay? So I think that's it. The groups, usually, what we do is we gather the groups together. We have 2 rooms available for that, okay? We have the meeting room in the 4th floor here. If you go to the end of the corridor, turning right, you have the first door is a meeting room. We have that one. And for that one, you need a password, okay, to open the room. And the password is 04019, okay, to open that room. It doesn't fit more than 1 group over there, okay? So it's kind of a small space. And the other one is our computer room, okay? So the computer room is also available for you along the whole week, okay? The computer room is more spacious, so it should fit 4 groups over there, even though it can get a little bit noisy, right, at some point. I don't know if we can use free classrooms, or no, we are forbidden to enter classrooms if they are free. Yeah. You know, people have classes in the first floor, right? So you have to be careful not to make too much noise for people taking classes. But if they are free, I think we can use. But there are classes sometimes from 2 to 4, from 4 to 6, right? So yeah. So you have to respect students here. Okay. So yeah. And that's it. Okay. I think I told everything. The auditorium as well. Yeah. Yeah, you can also use this auditorium. Yeah, okay. I think only tomorrow afternoon we cannot use because there's a seminar here. Yeah. Okay, questions, people. So I think you have lots of questions about the project and so on, but it's something that we keep talking through the whole week. Yeah? Okay, so time for lunch. Thank you.